What do heterogeneous cloud GPUs, graph benchmarks, and gene networks have in common? In this episode, we explore 3 papers that challenge assumptions in AI systems and scientific machine learning. One shows how to squeeze more performance from fragmented GPU fleets with clever LLM serving templates. Another reveals that simple graph invariants can rival powerful GNNs while exposing benchmark flaws. A third uncovers when causal gene network inference truly works and when correlation wins. Let's explore the first paper, Coral Cost-Efficient Multi-LLM Serving Over Heterogeneous Cloud GPUs. Coral targets a deployment regime where no single LLM dominates, and cloud GPU fleets are fragmented across H100, A100, L40S, L4, and A10G nodes with very different price-performance profiles. The paper's novelty is a joint optimization of resource allocation and model placement for multiple LLMs under per-model latency SLOs, instead of treating each replica as homogeneous. Coral proves this can be decomposed losslessly by pre-computing offline serving templates. For each model, SLO, and feasible node combination, it uses an ILP to find the throughput optimal hybrid pipeline, data parallel placement, then caches that placement as a reusable template. Online, a second ILP selects and instantiates templates across regions under real-time availability and pricing, reducing solve time from hours to tens of seconds. In evaluation, the online allocator averages 0.24s in the core setup and 9.68s in the extended setup, while the offline generator produces thousands to tens of thousands of templates per model SLO pair. Across 6 models, including Qwen 332B, GPT-OSS 20B, 5414B, Qwen 3235B, GPT-OSS 120B, and Llama 370B, and Van GPU configurations, Coral cuts serving costs by up to 2.79 times versus the best baseline, and raises goodput by up to 2.39% under scarce resources. Compared with Helix on a heterogeneous 6.4 GPU cluster, it lowers cost 21% and improves throughput 26% while meeting latency constraints. The key technical insight is that mixed GPU replicas, such as L40S plus H100 or A100 plus H100 serving templates, can fill throughput gaps and resolve cross-model contention that homogeneous or per-model greedy policies cannot. Let's explore the second paper, Invariant-Based Diagnostics for Graph Benchmarks. Invariant-based diagnostics for graph benchmarks argues that current graph benchmarks confound node features with connectivity, obscuring whether graph structure actually matters. The paper replaces learned graph encoders with permutation-invariant structural descriptors such as Wiener index, Laplacian spectrum, homomorphism counts, Foreman-Ricci curvature, and Balaban index, then evaluates them with XGBoost and a GIN encoder across 26 datasets. On the Breck expressivity benchmark, a small subset of 4 invariants matches the full invariant set and reaches 73% pair discrimination, outperforming all GNN-based baselines and approaching the 74.5% of the 2-hop count model N2. For dataset diagnostics, invariant fingerprints classify 23 datasets with 56.6% accuracy overall and 93.2% when restricted to representative datasets per domain, revealing strong structural shift even within domains. In a multitask setup on 12 datasets, higher meta-classification accuracy consistently predicts lower downstream performance and worse gradient alignment, with correlations such as negative 0.92 on base and negative 0.978 on proteins. In final benchmarks, invariant-based XGBoost is competitive with, and sometimes better than, transformer and message passing models. It reaches 79.7% on Colab, 77.4% on proteins, 82.4% aurok on base, 0.687 AP on peptides func, and cuts MAE on flow, easy from 3.44 with GIN to 1.83. The central claim is that expressivity alone is a weak predictor of task performance, and invariant baselines should become a standard diagnostic for deciding whether graph structure is truly needed. Let's explore the third paper. When does gene regulatory network inference break, a controlled diagnostic study of causal and correlational methods on single-cell data? This paper asks why causal gene regulatory network inference often loses to simple correlation on single-cell RNA-seq benchmarks, and answers it with a controlled diagnostic simulator rather than another leaderboard. The authors build a linear additive noise structural causal model, plus a nonlinear tan variant and sweep 7 independently tuned pathologies: dropout, latent confounders, cell type mixing, feedback loops, network density, sample size, and pseudo-time drift. Across 2,100 linear experiments and 6,120 total controlled runs, they compare Pearson correlation, mutual information with 6-bin discretization, Gini, 3 random forests, PC, GIS, and no tiers using undirected and directed AUPRC, plus an error type decomposition of true, reversed, confounded, spurious, and missed edges. The central result is that causal methods are genuinely best in clean regimes. No tiers reaches 0.992 undirected AUPRC and 0.989 directed AUPRC. GES reaches 0.944 and 0.911. But heavy dropout reverses the practical advantage, with MI and Gini 3 collapsing by about 0.69 and 0.67 AUPRC, while Pearson degrades much more slowly to 0.53. Latent confounders and cell type mixing compress all methods into narrow performance bands, showing that observational data alone cannot resolve hidden common causes. The error decomposition exposes why aggregate AUPRC is misleading. Structural methods more often produce confident, spurious, or confounded edges, whereas symmetric methods mostly fail by reversals and misses. An interaction sweep over dropout, confounding, and density finds sub-additive joint degradation and a density-dependent crossover, where GES overtakes Pearson under heavy dropout at density 0.3. The practical takeaway is specific. Use no tiers for sparse, well-sampled networks, Pearson under severe dropout, and interventional data when confounding is suspected. That's a wrap on today's AI paper highlights. Thanks for watching.